Find somewhere comfortable. Somewhere your body can be heavy. You do not need to follow any of this closely, and you do not need to remember a single word. Just let the sound of the voice arrive, the way a distant train arrives on a still night, felt before it is heard and gone again before you quite notice it leaving. We are in no hurry here. The night is long and patient, and so are we. If today was hard, you can set it down now. Whatever you carried through the hours, the worry, the weight of small things and large ones, the conversations that replayed themselves when you didn't ask them to, none of it needs to come with you into this hour. It can stay out there, beyond the door, beyond the dark. You are allowed to rest. Tonight we are going to descend, not in any way that requires effort from you. You will not be asked to concentrate or to follow an argument or to hold anything in your mind. We are simply going to travel, slowly and gently, down into the earth. Into a story about the deepest hole ever dug by human hands. A hole so deep that the rock at the bottom is older than almost anything you could name. A hole where the rules of the solid world began to soften and bend, where water appeared where there should have been none, where ancient life was found in the dark, patient and perfectly preserved, waiting 2 billion years to be discovered. It is a quiet story, a slow one. Let it wash over you the way the tide washes over stone. Not trying to move it, just touching it, again and again. So, wherever you are, let your weight settle into whatever is beneath you. And we begin. Somewhere in the far northwest of Russia, near the top of the world, on a treeless peninsula where the winters are long and the light behaves strangely, there is a rusted metal cap bolted to the ground. It is not particularly large. You could walk past it without stopping. It sits in a landscape of birch scrub and frost-cracked concrete, the remnants of a Soviet-era industrial compound slowly being reclaimed by the cold. The buildings around it have fallen in on themselves. Windows are gone. Floors have buckled. The machinery that once hummed and groaned here has long since gone silent. But beneath that cap, the ground opens into something extraordinary. A hole. A single narrow shaft descending 12 kilometers into the earth. 12 kilometers. More than 7 miles straight down. Deeper than any other point that human beings have ever physically reached on this planet. Deeper than the deepest trench in all the ocean. Deeper than Mount Everest and Mount Fuji placed one on top of the other and pushed beneath the surface. And yet, from the outside, it looks like almost nothing. A manhole cover, a bolt in the ground, the quiet lid of a very old ambition. The Kola Superdeep Borehole. That is its name. And the story of how it came to exist and what was found inside it is one of the gentler marvels of human curiosity. Not a story of conquest exactly, more a story of patience, of slow descent, of the earth refusing to be entirely known, and the scientists who kept going anyway. It began, as so many things did in the middle of the 20th century, with a competition no one had formally declared. The Americans, in the late 1950s, had a plan. They called it Project Mohole, and the idea was both elegant and audacious. The ocean floor, it turns out, is much thinner than the continental crust. In some places only 5 or 6 kilometers of rock before you reach the boundary between the crust and the mantle beneath. So American scientists proposed drilling through the seafloor, from a ship floating in the Pacific, all the way down through that thin oceanic crust to reach the mantle itself. to sample, for the first time in history, the material that makes up most of our planet's volume, to hold in their hands something that had never been touched, never been seen, never been anywhere near the surface. It was a beautiful idea. And for a while, it worked. Test drills were made off the coast of Mexico in 1961. Core samples came up from beneath the seafloor. Scientists were delighted, but the project was expensive and complicated, and eventually the United States Congress decided it could not justify the cost, and Project Borehole was cancelled in 1966 before it reached its goal. The Soviets were watching. On the 24th of May 1970, on the Kola Peninsula in what is now the far northwest of Russia, a drill bit touched the ground and began to turn. The site had been chosen carefully. They wanted to read the record of the Earth's interior, the way an archaeologist reads the layers of a dig site, slowly, attentively, with great care for what each stratum might reveal. The drilling rig that rose from the tundra was not the largest structure ever built, but it was purposeful. It had to be. The engineers knew from the beginning that what they were attempting had never been done. No one had drilled this deep into continental rock. No one really knew, in a practical sense, what they would find. In the early years, the work went relatively smoothly. The drill descended through the upper layers of the crust, and rock samples came up in cylinders. Cores, they are called. Each one a small window into a world that had been sealed away since before life grew complex on the surface above. The scientists examined these cores with tremendous care. They catalogued the minerals, measured the density, noted the temperature at each depth. They were building, meter by meter, a portrait of the Earth's interior that no seismic measurement taken from the surface could give them with quite this kind of intimacy. The drill itself was a remarkable piece of engineering. The conventional method of rotary drilling, spinning the entire length of pipe from the surface, was simply not possible here. The pipe would have weighed more than 1,000,000 pounds by the time it reached the depths they were aiming for. The torque required to spin it would have been impossible to generate, and the pipe itself would have twisted and snapped long before the drill bit reached its target. So the Soviets invented something different. A turbo drill. Instead of rotating the whole pipe, they designed a drill bit that spun at the very bottom of the string, powered by the pressure of drilling fluid pumped down from the surface. The fluid, a specialized mud, heavy and thick, served multiple purposes. It lubricated the bit. It carried the crushed rock fragments back up to the surface, where they could be collected and studied. And it helped cool the drill, which was generating tremendous heat as it ground its way through some of the hardest rock on Earth. New tools had to be built from scratch for this project. Logging instruments, devices lowered into the borehole to measure temperature, pressure, magnetic fields, and the density of the surrounding rock, had to be redesigned to function in conditions of heat and pressure that would destroy ordinary equipment. Everything had to be rethought. And the rethinking took time. Years passed. The drill descended through the 1970s. In 1979, it passed the depth of the Bertha Rogers hole in Oklahoma, which had been drilled in search of natural gas and had held the world record for deepest borehole. Now the Kola borehole was the deepest. And still it went down. By the early 1980s, the project had become something of an institution. The compound on the Kola Peninsula had its own community. Scientists, engineers, technicians, support staff, all living and working in this remote place, dedicated to the slow, patient work of going deeper. There were laboratories on site where cores were processed and analyzed. There were libraries of data growing year by year. There were friendships and rivalries and the particular camaraderie of people working together on something they know is unlikely to be finished in their lifetimes. The borehole by this point was extraordinarily narrow. At the surface it was about 92 centimeters wide. But as it descended, and as the drill bit was replaced and the pipe was adjusted and the borehole was lined and re-drilled in sections, it narrowed. At the deepest point it would eventually reach, it measured just 23 centimeters across, less than the width of a dinner plate. A crack in the earth, really. A whisker of a tunnel. And yet it went down 12 kilometers. Imagine lowering a piece of string into a glass of water. The string is thin. The glass is tall. Now imagine the glass is 7 miles deep. That is roughly the proportion of the Kola borehole. And into that narrow darkness, the drill kept turning. There is something quietly humbling about what the scientists found as the borehole deepened. Before the drilling began, geologists had a model of what the continental crust looked like from the inside. It was based on seismic data, on the way earthquake waves travel through the earth and bounce back to instruments on the surface. From this data, they had constructed a picture, a layered picture. Upper crust of granite, they believed. And then, at around 7 kilometers depth, a transition. The seismic waves changed behavior at that depth in a way that suggested the rock type shifted from granite to something denser. Basalt, most likely. A darker, heavier rock of the kind that makes up the ocean floors. This boundary had a name, the Conrad discontinuity. It was a feature that appeared in seismic surveys all over the world. It seemed real. It seemed well established. And the scientists drilling at Kola expected to pass through it to find themselves at around 7 kilometers drilling through basalt instead of granite. They kept drilling. 7 kilometers came and went. And the basalt never appeared. The rock at 7 kilometers was still granite. Or rather, something that had been granite, but had been altered by the immense heat and pressure of the deep earth into a different form. Metamorphic rock, geologists call it. Granite that had been squeezed and heated over millions of years until its crystal structure had rearranged itself. But it was not basalt. It was not a different rock type at all. The Conrad discontinuity, as it turned out, was not what anyone had thought. It was not a boundary between two different kinds of rock. It was something subtler. A boundary between two states of the same rock. A change in how the granite behaved under pressure, rather than a change in what the granite was. The seismic waves had been telling a true story, but geologists had been reading it incorrectly. This was not a small correction. This was a fundamental revision of how the continental crust was understood. Textbooks had to be rewritten. Models had to be rebuilt. And it happened not because of a new theory dreamed up in a university office, but because someone had actually gone down there and looked. The implications spread outward slowly, the way heat spreads through stone. If the Conrad discontinuity was misunderstood here, then perhaps the interpretation of seismic data everywhere needed to be revisited. Perhaps other features that appeared in seismic surveys, features that had been assumed to represent boundaries between different rock types, were also metamorphic transitions, not compositional ones. The Kola borehole had, in a single discovery, changed the way geologists read the language of the earth. And then there was the water. At depth, the rock was supposed to be dry. This was another assumption that had seemed reasonable, even obvious. At several kilometers below the surface, the pressure is so great and the temperature so high that any water present in the rock should have been driven out long ago, squeezed upward and away. The deep crust in this picture was a sealed, arid world. Hot and dark and dry. But at around 3 kilometers, And again at 6, and then deeper still, the scientists encountered something they had not expected. Hot, mineralized water. Not flowing water, not an underground river. But water nonetheless, trapped in tiny fractures and pores in the crystalline rock under enormous pressure, saturated with dissolved minerals. Water that had been there, sealed in the rock for an almost incomprehensible length of time. Where had it come from? Slowly. Over millions of years. And the water was being trapped as it formed, sealed in by layers of impermeable rock above. This finding reshaped the understanding of how water moves through the deep crust, and it raised questions, still only partially answered, about the role that deep crustal fluids play in the movement of minerals, in the behavior of faults, in the long, slow chemistry of the Earth's interior. There was also hydrogen. Unexpectedly large quantities of hydrogen gas bubbling up through the drilling mud as it returned to the surface. The drilling crews described the mud as boiling with it, along with helium, nitrogen, and carbon dioxide, gases that had no obvious source in the models of the crust that scientists had been working from, gases that suggested chemical reactions occurring in the deep rock that were not yet understood. The Earth, it seemed, was producing things that no one had predicted. It was not a passive, inert shell around a hot core. It was active, reactive, quietly generating and transforming materials in the dark. Of all the discoveries made at Kola, there is one that carries a particular quality of wonder, one that is harder to set aside even now, even years after the drilling stopped. At a depth of 6.7 kilometers, more than 4 miles below the surface, the scientists found life. Not living organisms, to be clear. Not bacteria moving through the rock, though that possibility has since become a serious area of research. What they found were fossils. Microfossils. The preserved remains of 24 species of microscopic plankton, single-celled organisms that had lived in ancient seas more than 2 billion years ago. 2 billion years. The number is almost impossible to hold in the mind. 2 billion years ago, the most complex life on Earth was single-celled. The continents were arranged in configurations that no longer exist. The atmosphere had a different composition. The sun was slightly dimmer, and these tiny organisms, these ancient plankton, were living in shallow seas, going about the slow business of life, and then dying, and sinking, and being buried so deeply over such an enormous span of time that they ended up more than 4 miles underground. What was extraordinary was not just that they were there. It was how well preserved they were. The microfossils were encased in organic compounds, carbon and nitrogen, that had protected them from the heat and pressure of the deep earth for those 2 billion years. Their structures were still recognizable. Their forms were still distinct. The scientists who examined them could identify the species, could say something about the environment those organisms had inhabited when they were alive. Think about what that means for a moment. A living thing, smaller than a grain of sand, preserved in rock for 2 billion years, discovered by a drill bit turning in the dark. The oldest trees alive today are perhaps 5,000 years old. These fossils were 400,000 times older than the oldest living tree. And they were still there, still recognizable, still telling a story. The discovery did something important to the scientific understanding of life's resilience. Before Kola, there was a general assumption that extreme heat and pressure would destroy organic material over geological timescales. The conditions at 6 kilometers depth, temperatures well above 100 degrees, pressures hundreds of times greater than at the surface, seemed incompatible with the preservation of anything as delicate as a biological structure. But the fossils at Kola said otherwise. They said that under the right circumstances, in the right chemical environment, life's traces could persist in conditions that seemed to make persistence impossible. This finding fed directly into a growing field of research that has only expanded in the decades since: the study of deep life. Bacteria have been found in boreholes and mines at depths of several kilometers, living in conditions of heat and pressure and chemical extremity that would kill any surface organism. They live slowly. They metabolize at rates so low that a single cell might reproduce only once in thousands of years. But they live. And the implications of this extend outward, beyond the Earth. If life can persist in such extreme conditions here, in the hot, pressurized, mineral-saturated darkness of the deep crust, then perhaps life can persist in similar conditions elsewhere. On Mars, where liquid water may once have existed deep underground and may still exist in some form. On Europa, Jupiter's moon, where a vast ocean is thought to be sealed beneath a thick shell of ice. On Enceladus, Saturn's moon, where geysers of water vapor erupt from cracks in the surface, suggesting a warm, liquid interior. The ancient plankton found at Kola, silent in the rock for 2 billion years, opened a door that has not been closed since. In 1989, the drill at Kola reached its greatest depth, 12,262 meters, 40,230 feet. 7.6 miles. And then it stopped. Not because the scientists had reached their goal, not because they had found what they were looking for, or decided they had gone far enough. The drill stopped because the Earth stopped cooperating. The temperature at that depth was 180 degrees Celsius, 356 degrees Fahrenheit. Hot enough to sterilize surgical instruments, hot enough to melt certain plastics, hot enough to destroy the seals and bearings in the drilling equipment within hours of exposure. This temperature was nearly double what the scientists had predicted. Their models, based on the best available data about how heat increases with depth in the continental crust, had suggested temperatures of around 100 degrees Celsius at 12 kilometers. 100 degrees is hot, but it is manageable. Equipment can be designed to handle 100 degrees. 180 is a different matter entirely. The reason the prediction was so wrong comes back to the water. The trapped fluids in the deep rock were carrying heat upward through the crust, transferring thermal energy far more efficiently than solid rock alone would do. The geothermal gradient, the rate at which temperature increases with depth, was much steeper than the models had accounted for, precisely because of the fluid circulation that no one had known to include in those models. And the heat had another effect, one that was perhaps even more practically consequential. At those temperatures, the rock began to behave differently. Granite, under normal surface conditions, is one of the hardest materials on Earth. It fractures under stress. It breaks. But at the temperatures and pressures found at 12 kilometers depth, granite becomes something else. It becomes plastic, not liquid, but not quite solid in the ordinary sense either. It deforms slowly under pressure, the way warm clay deforms when you press your thumb into it, without cracking. And what this meant for the borehole was that the walls of the hole were creeping inward. The borehole was not stable. The rock around it was slowly flowing under its own weight, narrowing the shaft, deforming the casing, threatening to close the hole entirely. Equipment lowered into the borehole was at risk of being trapped, swallowed by the plastic rock closing around it. Several times in the final years of drilling, equipment was indeed lost, stuck fast in the narrowing shaft, impossible to retrieve. The scientists tried for several years after 1989 to push deeper. They redesigned equipment. They developed new high-temperature drill bits and thermostable lubricants. They tried drilling a new branch of the borehole at a slightly different angle, hoping to find conditions that were slightly more manageable. But the heat was implacable. The rock would not yield. In 1992, drilling was formally suspended. The project continued in a reduced capacity for a few more years, analyzing the cores that had already been brought up, publishing findings, trying to extract the maximum scientific value from what had already been achieved. But the drill itself never went deeper. In 1995, the project was officially closed. The Soviet Union, which had funded it, no longer existed. Russia, in the economic upheaval of the 1990s, had other priorities. By 2008, the site was fully abandoned. The wellhead was sealed with a heavy metal cap. The rusted disc that sits there still, bolted to the ground, covering the deepest hole that human beings have ever made. And here is something worth sitting with for a moment. Something that speaks to the scale of what lies beneath us. 12 kilometers, 7.5 miles. The deepest point any human instrument has ever physically reached within the solid earth. And yet the distance to the center of the planet is more than 6,000 kilometers. The Kola borehole penetrated less than 1/3 of the continental crust at that location. The crust itself is only the thinnest outer skin of the planet. Below the crust is the mantle, nearly 3,000 kilometers of rock, behaving over geological time like an extraordinarily viscous fluid, convecting slowly, carrying heat upward from the core. And below the mantle, the core, iron and nickel, partly solid, partly liquid, generating the magnetic field that shields the surface from solar radiation. None of that was reached. None of it was even closely approached. We know more about the surface of the moon than we know about the inside of our own planet. We have better maps of Mars than of the deep Earth. The ground beneath your feet is, in a real and important sense, more mysterious than the sky above your head. There is a story that used to circulate about the Kola borehole. A story that spread through tabloids and newsletters and, later, across the early internet. It claimed that when scientists lowered a microphone into the borehole, they heard sounds rising from the depths. Sounds that could only be described as voices. Thousands of voices crying out together. The scientists, the story claimed, were so disturbed by what they heard that they abandoned the project immediately. They had drilled into hell, the story said. They had heard the screaming of the damned. It is, of course, not true. The project ended because of heat and pressure and the slow failure of equipment and the dissolution of the Soviet Union and the ordinary, unglamorous exhaustion of money and political will. There were no screaming voices. There was no microphone lowered into the dark. But the story persists, and it is worth wondering for a moment why. Why this particular myth attached itself to this particular place. Why the idea of a hole in the ground, deep enough, should summon in the human imagination the image of another world beneath our feet. A world of heat and suffering and ancient, trapped things. Perhaps it is because the earth beneath us is genuinely mysterious, genuinely unknowable, in a way that the sky is not. We can see the sky. We can send machines into it, and they return. We can look at distant stars with instruments that bring them closer, but the ground beneath us is sealed. It does not give itself up easily. You can drill into it for 20 years with the combined resources of a superpower and reach only a tiny fraction of the way to its center. There is something in that opacity that the mind wants to fill. And what the mind fills it with says something about what we carry inside ourselves. The old fears, the old stories, the sense that beneath the ordinary surface of things there is something vast and ancient and not entirely benign. The actual story of the Kola borehole is quieter than that. But in its own way, it is stranger. Ancient plankton in the rock. Water where there should be none. Hydrogen bubbling up from the depths. Granite that becomes soft as clay when the pressure is high enough. A hole so narrow you could not lower your arm into it, going down farther than any human being has ever physically gone below the surface of this planet. The Earth is old, older than almost anything the mind can accommodate. The rocks at the bottom of the Kola borehole are 2.7 billion years old. When those rocks were formed, the sun was already middle-aged. Single-celled life existed on the surface, but nothing more complex. The continents were in entirely different positions. The chemistry of the ocean was different. The length of the day was different. The Earth rotated faster then, and a day lasted only about 18 hours. And those rocks have been sitting there, in the dark, under enormous pressure, since before any of the creatures that now share this planet with us had come into existence. Since before fish, since before trees, since before insects, since before the extinction of the dinosaurs, which happened a mere 66 million years ago. A blink in the timescale of those rocks. There is something calming in that, if you let it land gently. The sense that the ground beneath you is ancient beyond comprehension. That it was here long before you and will be here long after. That whatever you are carrying tonight, whatever the day left behind in your body, in your chest, in the quiet space behind your eyes, it is very small against the age of the rock, not small in a diminishing way, small in a restful way. The way a single breath is small against the depth of the ocean, the breath still matters. But the ocean is very large. The cores from the Kola borehole still exist. Many of them are stored in a repository, cylinders of ancient rock stacked in trays, waiting for future scientists with better tools and new questions to examine them. Dr. Ulrich Harms, a geologist who visited the site and the core repository years after the project ended, described the experience as quietly moving. All of that rock, all of that patient descent, all of that accumulated evidence of the Earth's interior, sitting in boxes in a room, largely unstudied, waiting. New analytical techniques are applied to the Kola cores every few years. Methods that did not exist when the drilling was done. Ways of measuring isotopic ratios, of imaging crystal structures, of detecting trace elements at concentrations that older instruments could not resolve. Each new pass through the data tends to produce something. A refinement of understanding, a new question, a small correction to the models. The hole is sealed and the compound is abandoned, and the compound is being slowly consumed by weather and time. But the knowledge keeps working. China, in recent years, has been pursuing its own deep drilling program. In March of 2024, a borehole in the Tarim Basin in western China passed 10,000 meters. By early 2025, it had reached 10,910 meters, the deepest borehole in a sedimentary basin ever completed. It does not yet surpass Kola's 12,000 meters of true vertical depth in crystalline rock, but it is getting closer. and the scientists drilling it are drawing on everything that was learned at Kola. The thermal models, the fluid dynamics, the equipment designs, the hard-won understanding of how rock behaves when you push it to its limits. The project that began in the Soviet Union, on a cold peninsula at the top of the world, on a May morning in 1970, is still reverberating through the science of the Earth. Still producing. Still teaching. And somewhere beneath you right now, as you lie in the quiet dark, the rock is ancient and patient and warm. Not warm the way a hand is warm, warm the way the deep earth is warm, slowly, steadily, with a heat that has been building since the planet formed 4.5 billion years ago, a warmth that does not hurry, that does not ask anything of you. That simply persists beneath the soil and the stone, down through the kilometers of compressed rock, down past the depth that any drill has ever reached, down into the vast interior of the world. You are resting on something very old tonight, something that has been here through everything, through the rising and falling of mountains, through the opening and closing of oceans, through ice ages and warm periods and the slow drift of continents, through the appearance of life, its diversification, its long unfolding into the extraordinary complexity of the world you know. The ground is patient. It will hold you. The researchers who worked at Kola, the geologists and engineers and technicians who spent years in that cold, remote place, drilling slowly into the unknown, they understood something about patience, about the value of the long, unhurried pursuit of something that may not yield quickly and may not yield completely, but that rewards the effort with occasional glimpses of something genuinely new. A layer of rock that wasn't supposed to be there, a pocket of water in the dry deep, a tiny fossil preserved against all expectation, 2 billion years in the making. They kept going not because they were certain of what they would find. They kept going because the question itself was worth asking. What is down there? What does the earth look like from the inside? What does the rock tell us if we are willing to listen? And the earth, slowly, in its own time, began to answer. The metal cap is still there on the Kola Peninsula, and beneath the cap, the borehole descends, narrow and dark and still, all the way down through the ancient rock, past the depth where water was found, where no water should be, past the depth where 2 billion-year-old plankton waited in their stone, past the depth where granite grows soft as warm clay, down to the deepest point any human instrument has ever rested inside this planet. It is quiet down there now. It has been quiet for a long time. And so we leave it there in the deep and patient dark. The day is already far behind you. The weight of it has grown distant. Somewhere beneath you, the old rock holds its warmth, unhurried, as it has always done. Drift now, if you're ready. Sleep well. There is a detail about the drilling process that is easy to overlook, but that stayed with many of the scientists who worked at Kola long after the project ended. The cores, those cylinders of rock brought up from the depths, did not arrive looking like rock. Not exactly. They arrived looking like rock that had been somewhere else. Somewhere that was not here, not the surface, not the ordinary world of weather and light and air. They were warm to the touch, sometimes hot, and when they were brought into the surface air, they would sometimes crack. Not dramatically, not explosively, but with a quiet ticking sound as the pressure that had held them compressed for billions of years was suddenly released. The rock was adjusting to a world it had never known, decompressing, settling into a new state. The scientists who handled those cores were, in a very real sense, the first living things to ever come into contact with that material. The first to touch it, to smell it, to hold it under a light. There is something in that which is worth sitting with, a piece of the deep earth, ancient beyond any frame of reference most of us carry, being held in a human hand for the first time in the history of the planet. Some of the cores were stored carefully in temperature-controlled conditions, catalogued and labeled and set aside for future study. Others were analyzed immediately, on-site, in the laboratories that had been built within the compound. The scientists worked with the methodical patience of people who understood that what they were examining had taken an unimaginable length of time to form and deserved a corresponding care in the examination. The borehole itself had to be maintained constantly. Drilling fluid, that heavy, specialized mud, was pumped down continuously, not only to cool and lubricate the drill bit, but to keep the walls of the hole from collapsing. The pressure of the surrounding rock was always pressing inward. The borehole was, in a sense, a temporary wound in the earth, held open by engineering and chemistry and continuous effort. The moment that effort ceased, even briefly, the rock began to reclaim its space. There were setbacks. In 1984, while drilling through a particularly difficult section of fractured rock, the drill string became stuck. The pipe had to be cut, and a new branch of the borehole was started from a depth of 7,000 meters, angling slightly away from the original path. This added years to the project and required a redesign of portions of the drilling program. But the scientists adapted. The work continued. The patience of the project was one of its defining qualities. The hydrogen that bubbled up through the drilling mud at Kola deserves a little more attention because it points towards something that scientists are still actively investigating today. On the surface of the Earth, hydrogen gas is not something you encounter in its pure form very often. It is the most abundant element in the universe, but on our planet it tends to be locked away in chemical compounds, in water, in organic molecules, in minerals. Free hydrogen, rising through rock, was not something the geologists at Kola had expected to find in any significant quantity. The leading explanation involves a process called serpentinization, when certain iron and magnesium-rich minerals, olivine and pyroxene, common in the deep crust and mantle, come into contact with hot water. They react. They transform into a new mineral called serpentine, and in the process they release hydrogen gas. The reaction is slow. It happens over geological timescales, but it is steady and it produces hydrogen in quantities that, over millions of years, can accumulate. What makes this finding so interesting to contemporary scientists is its connection to the question of life in the deep earth. Hydrogen is an energy source. Certain microorganisms, chemolithotrophs they are called, organisms that derive energy from chemical reactions rather than from sunlight, can use hydrogen as fuel. They combine it with carbon dioxide to produce methane and water, releasing energy in the process. They live in the dark, in the heat, in the deep rock, sustained entirely by chemistry. The discovery of unexpected hydrogen at Kola, combined with the evidence of ancient preserved organic material in the cores, helped lay some of the intellectual groundwork for the deep biosphere research that has flourished in the decades since. If hydrogen was being produced by the rock itself, and if that hydrogen could sustain microbial life, then the deep crust was not the sterile, inert environment it had been assumed to be. It was, potentially, a habitat. A slow, dark, pressurized habitat, nothing like anything on the surface, but a habitat nonetheless. The hydrogen findings at Kola also fed into discussions about the formation of hydrocarbons, oil and natural gas in the deep earth. The conventional understanding of petroleum geology holds that oil and gas are biological in origin, formed from the compressed remains of ancient marine organisms. But some scientists have long argued for an additional, non-biological source, the production of hydrocarbons through chemical reactions in the deep crust, including reactions involving hydrogen and the mineralized water. That unexpected fluid, found sealed in fractures throughout the deep rock, turned out to carry its own remarkable record. Dissolved within it were concentrations of helium, argon, and other noble gases in isotopic ratios that told scientists something about when the water had last been in contact with the surface and how long it had been sealed in the rock. Some of the water appeared to have been isolated for hundreds of millions of years, trapped since before the age of the dinosaurs. Sitting in its tiny pocket of stone, under enormous pressure, in complete darkness, while the world above it was transformed beyond recognition again and again. The microfossils found at Kola were not the only biological surprise in the cause. At various depths, the scientists also detected complex organic molecules, long carbon chains, the kind that form the building blocks of biological material. These molecules were not fossils in the strict sense. They were chemical traces. Residues, the molecular memory of life that had existed, been buried, been transformed by heat and pressure over billions of years, and yet had not entirely disappeared. This finding pointed towards something that has since become a significant area of study in geochemistry, the way that organic carbon cycles through the deep earth. When living organisms die on the surface and their remains are buried, some of that carbon is eventually carried deep into the crust through geological processes, through the subduction of oceanic plates, through the slow burial of sediment. Down in the hot deep, that carbon is transformed. Some of it becomes graphite. Some of it participates in chemical reactions that produce new compounds. Some of it, apparently, survives in forms that are still recognizable as biological in origin even after billions of years. The carbon cycle, in other words, extends far deeper into the earth than most people realize. It is not just a surface phenomenon, not just photosynthesis and respiration and decomposition. It reaches down into the deep crust, into the mantle, and back up again through volcanic eruptions and hydrothermal vents. The carbon in the air you are breathing right now has, over geological time, cycled through the deep earth many times. It has been rock. It has been ocean. It has been the body of an ancient organism. It has been gas rising from a volcano. The journey is long and slow and almost impossibly complex, and the Kola cores offered a small but vivid glimpse into one part of it. There is a researcher named Tullis Onstott, a geologist at Princeton, who has spent much of his career studying life in the deep earth. He and his colleagues have found living bacteria in South African gold mines at depths of nearly 4 kilometers, in water that had been sealed in the rock for millions of years. The bacteria were metabolizing so slowly that a single generation, the time it took for one cell to divide into two, was estimated at perhaps 10,000 years. 10,000 years for a single act of reproduction. And yet, the bacteria were alive, functioning, going about the ancient, patient business of being. Onstott has spoken about the experience of finding these organisms as quietly profound, the idea that life, having once taken hold in a place, will persist there through almost any change in conditions, adjusting its pace, slowing to almost nothing if necessary, but not giving up. Says something he has suggested about the tenacity that is woven into living things at their most fundamental level. The bacteria in the deep rock did not know that the surface world existed. They did not know about the sun or the atmosphere or the extraordinary diversity of life that had emerged above them over hundreds of millions of years. They simply continued. In the dark, in the heat, one slow division at a time, the ancient plankton of Kola, preserved in their stone for 2 billion years, were no longer alive. But they were the ancestors, in a sense, of everything. Every organism that has ever lived on this planet is descended from organisms like them, from the single-celled life of the early Earth, slowly evolving, slowly complexifying, over an almost unimaginable span of time. The fossils in the rock were a kind of root, a reminder of where all of this began. There were people who gave significant portions of their lives to the Kola project. Scientists who arrived as young researchers in the early 1970s and were still there in the late 1980s, grey-haired, their careers shaped entirely by this one long, slow, deep endeavour. One of them, a geologist named David Guberman, worked on the project for years and later described the experience of working at Kola as unlike anything else in science. The slowness of it, he said. The way progress was measured not in days or weeks but in meters, and sometimes in fractions of meters. The way a single core sample could represent months of effort. The way the Earth pushed back, constantly, quietly, requiring patience and ingenuity and a willingness to be surprised. He described the compound on the Kola Peninsula as having a particular atmosphere. Remote, certainly. Cold for much of the year. But also purposeful. Everyone there understood that they were engaged in something that had never been attempted and that the results would matter. Not immediately, not in ways that would be announced in headlines, but slowly, over years and decades, as the data was analyzed and published and absorbed into the body of geological knowledge. There was a satisfaction in that, he said, that was different from the satisfaction of faster science. A quieter satisfaction. The satisfaction of the long view. The compound itself was a small world. There were families there. Some scientists brought their spouses and children to live in the housing provided on site. There were schools and a medical clinic and a canteen. There were evenings when, in the brief northern summer, the sun barely set and the light turned golden and strange over the treeless landscape, and people sat outside and talked, the way people talk when they are far from the rest of the world and have made a kind of peace with that distance. And then it ended. Not with ceremony, not with a formal conclusion or a celebration. It ended the way so many things end, gradually and then suddenly. The funding diminished. The staff dispersed. The equipment was left in place because there was no budget to remove it. The buildings were locked, and then the locks rusted, and then the buildings were simply left to the weather. A photographer named Rakot Lean documented the site in the years after its abandonment, and the images carry a particular quality. The drilling rig still standing, weathered but intact against the pale sky. The laboratories with their equipment still on the benches, as though the scientists had simply stepped out for a moment. The core storage rooms with their trays of rock cylinders, dusty now, the labels fading. Everything preserved in a kind of accidental stillness. Not curated, not maintained. Just left, the way a room is sometimes left when the leaving is too abrupt for tidying. There is a word in Portuguese, saudade. That describes a particular kind of longing for something that is gone or perhaps never quite existed as you remember it. A tender ache. The photographs of the abandoned Kola compound carry something of that quality. Not grief, exactly, not loss in any dramatic sense, just the quiet recognition that something was here and was real and mattered and is now still. The knowledge persists. The cores persist in their repository, waiting. The papers published by the Kola scientists have been cited thousands of times in the decades since. The questions the project raised about deep fluids, about the geothermal gradient, about the behavior of rock under extreme conditions, are still being pursued by researchers around the world. In Iceland, where the geology is young and active and the heat of the earth comes close to the surface, scientists have drilled into magma chambers and studied the boundary between rock and liquid at depths no one had reached before. In Scandinavia, new boreholes are being planned to study the deep crust of the Baltic Shield, the same ancient rock that the Kola drill descended through. In the United States, a program called the International Continental Scientific Drilling Program continues to fund deep drilling projects, drawing on the methods and lessons of Kola. The ambition that began on that cold peninsula in 1970 has not ended. It has distributed itself. It has become part of how the science of the earth is done. And perhaps that is how the most patient ambitions always work. Not arriving at a single destination, not planting a flag and declaring completion, but dispersing slowly into the work of others, becoming part of something larger and longer than any single project could contain. The way a river, when it reaches the sea, does not end. It simply becomes the sea, and the sea becomes the cloud, and the cloud becomes the rain, and the rain finds its way back to the mountains where rivers begin. The drill at Kola went down 12 kilometers and stopped. But the questions it asked are still descending,